Behind is the computer room where we used to have a large mainframe computer. Well, large in comparative terms. I mean, it's physically large. I don't think it's particularly brilliant. And it's now what's called cloud of PC processors. Cloud of processors replaced that. But it is the main depository for computing power and for data storage. The first pulse, I'm told, the data fitted on a floppy disk, 1.4 meg. Now, what was the last date I was given? 2005, I think, they were taking about 80 gigabytes. And the estimate was we'd be to out to 160 gigabytes per pulse now. So we'd fill a hard disk with every pulse. And we pulse from 6 in the morning to 12 at night, and doing a pulse every half hour on a really good day. So you can have 20 or 30 pulses. So the data gathering and the data storage becomes a really significant problem. I'm told that the value of the data that JET has gathered over the years is put at £2 billion, because that's roughly what it's cost to generate the data. And there are physicists working, going right the way back to all the data through all these tens of years of work, looking for a particular aspect of a particular type of plasma, of a particular type of reaction or instability, to gather more and more data for their papers and for an effort to overcome a problem with the plasma. Now, the plasma is held in place by the TF coil. The TF coils go round the torus. So there's a whole series of these coils, and they basically keep the plasma in place. But it's a bit like a group of small children holding onto a balloon. And these balloons that you make models from, you can have a load of children in a circle, you make one into a ring, and they all put their hands on and they squeeze. If you just touch it, that's fine. But if you start squeezing, eventually what happens is the balloon pops out between a pair of hands. And this is what plasma does between the TF coils. It is positively unstable. It always wants to escape the magnetic confinement. And so you're always having to chase it. And the PF coils actually position the plasma up and down or in and out. And the TF coils keep it away from the walls, basically. And the control mechanisms that have been developed to JET over the years to try and control the plasma enable you to keep the plasma in the middle of the torus, more or less. If it gets too far out from the side of the torus and touches the wall, it then loses its energy and can go out. And it will go out in milliseconds, what's called a disruption. Now, you've had all this magnetic force pushing on it, and everything's up to field strength, if you like, and then the plasma suddenly disappears. There's a hell of a bang as the machine relaxes because it's got nothing to fight against. It's called a disruption, and one of the first disruptions was over 400 tons force generated in the machine, and the machine moved 8 millimeters on its mounts in a big bang, and they picked the signal up at the seismological laboratory in the middle of Oxford and phoned up and said, what's going on? As, the earth just shook. And because that potentially could have done bad damage to the machine now has a lot of hydraulic dampers which actually control disruptions, what happens in the event of a disruption, like brakes. And the physicist is limited as to how big a disruption he potentially can cause. When you analyze a plasma, you can say just how big a disruption is going to be. An amateur physicist, if you like, or someone who's learning to operate a machine, will be limited to, say, 100-ton disruptions, which are thuds, basically. And then, a more senior one can have 200 tons, which are a bang. And then the really senior ones, in theory, can go back up to several hundred tons, which are a big bang. You have a microphone from the torus hall into here, so you can actually physically hear the bang when it happens, which is a bit worrying, particularly if you've got an engineer in charge, because those are the times that either electrical feed-throughs will break or water pipes will fracture, and you then might have either a loss of connection, you may get a loss of vacuum, or you may get water in the vessel. Now, the vessel's kept about gas mark 6, which is 200 degrees centigrade. That's to keep the vacuum nice and clean. So it's kept hot by a double wall arrangement. You saw the wall of the vessel. Round it is a layer of gas, which is kept heated and pumped round. And then there's that huge structure, which I showed you, the big cast structure you saw in the assembly hall. That's the gap where the heating system keeps the vessel at temperature. We can bake it to higher temperatures to clean it up at the beginning of a session, but the whole vessel, everything is kept about 200 C. So when we have the energy going in of these neutrons going into the machine and the energy of all the coils being energized, everything gets hot. So we can't run for very long before things are going into the overheat mode. We have to stop and let everything cool down again. Okay, I think we'll go. Are there any questions? Everybody happy? Yeah. Good. Okay, we'll go back down to the model.